Welcome to our mini course of deep learning, language models. 说欢迎大家来我们今天的深度自然语言处理。So this will be a 3 weeks mini course. First week, we are going to talk about the transformers and the GPT. We'll start with the transformer and the GPTs. There are two parts in this lecture. The first one is pretty simple. We're going to use Hugging Face transformer and load some model to see how it works. And the second part is we are going to explain how the code works. How GPT works. So we are going to compare the paper, the transformers paper, and our implementations of GPT. So you can see that in our course website, I have listed a video streaming in the last semester's course, deep generative models. That is we're talking about deep learning and deep learning with language models. So I have a live coding session to code a GPT-2. 所以去年的时候，我们课程里头有一个，就是在深度生成模型里头有 GPT-2， 我们有现场示范了一下怎么去撰写 GPT-2。那这是我们第二个部分会说明的地方。Okay, so let's begin with our first part. Let me get my Visual Studio Code right here. Okay, here is a simple sample of using the Hugging Face transformer. And here is our implementation, the NumPy implementation. I switched the font size a little bit smaller so that I can see the whole thing. So this is our GPT-2 implementation totally in NumPy. So before we show that, let me show you how this one, tiny GPT. So in fact, GPT, the implementation GPT is quite simple. I can actually put them in just like 20 lines. This is a whole implementation of GPT-2. 所以你看到，如果我们真的要写比较短的话，我用 NumPy 可以从这个第37行到这第60行，这已经是一个完整的 GPT-2 的GPT 基本上 GPT-2 啦，但 GPT-3 因为它没有放出来，可是它差不多是用一样的东西，所以这是一个完整的 GPT-2 的实作。So you can see that from the line 37 to line 60, this is a full implementation of GPT-2. There are some code before this one, before the line 37. And from line 15 to line 35 is an implementation of reading the safe tensor weight. Because a lot of the deep learning models, they publish their weight in safe tensor. So this is a full implementation of safe tensor, parser, and loader. So although you can see that this code is not very readable, I intentionally write it in a more compact form to instead of making it more readable, so that we can squeeze a whole thing inside like in 25 lines. However, even with a more readable implementation, right here is a full implementation. The GPT-2, I think this is a GPT-2 NumPy implementation or GPT-2, either way. Either one is a good one. So even with, to make it more readable, I intentionally make it more readable in this version. It still takes less than 100 lines. And you can see that a lot of lines is implement something like softmax or Jiru. Jiru is something like a Riru. It's an activation function. And you can see that the code is still very short and clear to understand. We will explain it and compare it with the transformer paper. 好，所以你可以看到它的程式码，即使是我们把它写成比较容易读的形式，它其实也不长。那我们会把它跟 transformer 的 paper 真的把它去对比下来。So the reason that I'm putting it in this way so that you can compare with transformer paper is because actually it helps you to read the source code of the Hugging Face implementation. 所以其实可以帮助你直接去读 Hugging Face implementation. Also, we have given a link to the original GPT-2 source code published by OpenAI. Okay, so let me show you the browser here. So here is, you can see that this is a GitHub repo from OpenAI. This is the reference implementation of GPT-2. The code is quite readable. So you can see that there are a lot of different implementation of GPT-2, like mini GPT, maybe a micro GPT, or like tiny GPT. Okay, min GPT. It's a min GPT. You can see this is implementation from Capacity. He has a min GPT and maybe another one. He used the PyTorch to implementation the GPT. You may wonder, okay, he is kind of like a coding god. He write a lot of great things. But in fact, you can actually do the same from scratch. The reason is that the OpenAI actually published the reference implementation of GPT-2. 所以虽然那个 Capacity 是一个大神，然后他写那个东西看起来好像很厉害，的确也蛮厉害的，没有错。但这完全是你可以办到的事情因为 OpenAI 它有把 GPT-2 的 source code 把它 release 出来 ，Hugging Face 里头也有类似的东西，只是比较难追一点点。所以这些东西完全都是你可以去使用的东西。So before we'll talk about how to use transformers and Hugging Face to load some model. Let's first mention some of the popular frameworks that people use to run large language models. The first one is Ollama. Ollama is a very convenient way. It's probably the most beginner-friendly way that you can run the large language model. It has already a lot of models provided. You can search the models in its homepage, and here, like if you want to find the QWin, which is one of the popular model, you just search QWin. And from its model repository, you can find all the possible models. And if you want to find like Llama 3.2, you just simply search Llama 3.2, and you can find Llama 3.2 here. You can run it quite easily. We will talk about it later. 所以如果你是初学者的话 ，Ollama 算是一个还不错的起始点。但是它有缺点， 它的模型有它特别的格式，不过它有整理好了，然后它的模型可能稍微少一点点，一些额外的模型你必须要重新的去 convert， 从其他地方 convert， 那会有一些麻烦的地方。但是它已经包含了很多的模型，像是 Gemma， 然后 Llama 这边都有。One of the drawback of Llama is you have to use Llama format of model that you can only use certain format of models. However, the collection of models provided in this repository in its official website is large enough. However, the models something like the Llama 3.2 11B vision. It doesn't have an 11B vision, or like even bigger one, like 90B vision. So you can see right here, it has 3B and 1B. In short, a lot of different choices you can choose from. However, it doesn't have 11B vision, which you might be interested. Okay, so this is one thing that you can, but it is very good for you, for beginner, to try it without too much hassle. And it has a command line interface so that you can interact with it to try it in a very quick way. 好，另外一个是 VLLM. Another one is VLLM. VLLM is also quite easy to install, and it supports Hugging Face models, which we will show you a little bit later. And it actually also provides a compatibility interface so that you can call an OpenAI-like API to interact, to access other open source models like Llama or Qwen or maybe Gemma. VLLM 是另外一个也还蛮容易去安装的东西。那它的优点是它可以直接使用 Hugging Face 里头你看到的所有的模型，它大部分都可以用。如果你该安装的东西都安装好的话，而且它的另外一个优点是它有提供像是 OpenAI 的 API 的界面，也就是说你可以像是如果你已经有一些去code ChatGPT 的程式码的时候， VLM 架起来它会有一个 API 让你可以去打它，那你可以完全使用像是 ChatGPT 那样子你去呼叫 ChatGPT 的 API 的那个方式去使用其他的模型，像是 Llama、Gemma 或者是像是我觉得 Qwen 也是一个还不错的模型。Okay, so this is another choice. And there's also some other things. Okay, one thing I haven't mentioned is that Llama is using Llama CPP. So one of the popular inference engine of LLM is Llama CPP. So this is one of the popular engine. Quite fast. There are a lot of different engines. I think Llama is using Llama.cpp behind the scenes. So if Llama, the convenience and accessibility is not your thing, maybe you can try Llama.cpp directly, because it also has something like Llama, libllama and the Llama server. And if Llama is all you want, the Meta, which is the company behind the Llama model, also provide a Llama stake. You can see that this is Meta. ，it is llama stake。所以 Facebook 或者说就是 Meta， 他们开发的是 llama 这个模型嘛，他们其实也有提供 llama stake 这一套东西，它可以做 serving 啊，可以做很多，就有点点像是 Llama 或者 VLM 在做的事情。However, I think llama stake is quite confusing and a little bit difficult to install. I have installed it and built a few model servering, but I haven't used it for real things because I couldn't see the benefit of using it comparing to using like Llama or VLM yet. So although it seems to be quite interesting and I'm sure it is solving some very real issues people actually facing, but I haven't figured it out yet. 所以这个 llama stake 安装起来挺困难的，我有安装起来，然后有 build 的一些东西，玩了一下，但是我还是比较习惯 VLM 或者是那个 Llama。你可以看到它这边也会有一些不同的 backend， 像是 Torch、VLM、TensorRT。所以我们目前的设定下面并没有特别用到 llama stake 的优势。我不太确定它优势在什么地方，可能是它可能分散式处理啊，或者是一些 serving 上面有一些优势，但是我可能目前没有用到，所以目前我比较常用的还是 VLM 跟 Llama 比较多。那除此之外there are also something else like LM Studio. There's also LM Studio, which is also very popular. And you may use something which I recommend before is like text web UI, text generation web UI, a Gradio web UI. I think people may still use it, but I haven't used it for quite a while. However, it still have some benefit because it supports a lot of different backend like Transformer, Llama CPP, X, Llama V2. TensorRT LLM, Auto GPTQ, and Auto AWQ. Any backend you can name of it kind of have sort of support, and it has a web user web interface. So I think it's still quite useful. But I think the reason that I didn't use it that much is because perhaps recently we are more focusing on programmatic using the language model instead of just trying out different things. So and I think the ecosystem is growing bigger and bigger for the large language model. So even if you just stick with just one of the backend like Llama CPP, just like Llama, or maybe you just stick with the transformers, you still get enough number of the models, pretty much every model we wish to try. 所以最近我比较少用这个 text web UI， 因为你可以看到它其实支援了很多很多不同的 backend， 像是很多不同的quantification 的，就是把它压成4个 bit 或者2个 bit， 或者是这种各式各样不同的，它都有支援。但是它的优点是在于它有一个 Web UI， 你可以快速去使用它。可是可能最近我们比较偏向习惯用写程式自动化的方法去 code， 而且整个生态系变大了，就算你只用一种 backend， 大部分的模型大概都可以去用它，所以这可能是比较少用到它的一些理由。那如果想要快速尝试的话，我可能会使用像是 Hugging Face 上面直接去试新的 model， 上面也有 Web UI， 我就不用自己再 download 的去架它，因为它模型的大小其实还挺大的。Okay, so if you want to really quick to try some model with some web user interface, I probably will use Hugging Face or using Hugging Face. There's a demo site, and maybe try it on Colab or other place instead of install it on my own machine. Because you see that the checkpoint, the weight of a large language model is quite actually large. For a 7B model, you probably get something like 14 gigabytes or even like 20 or near 30 gigabytes memory. So if you try a lot of different models, even you simply try some toward the model towards smaller side, middle size to towards side, like 7B models, it may require like 7 gigabytes up to 30 gigabytes memory storage. So if you try like 20 or 10, 30 models, it will like occupy your 300 gigabytes storage, which is not a small amount of storage, and it takes some time to download all these things. So if I want to try some model really quick, I'd like to try some queuing models, especially for some large models like 17B models. I probably will first try it on Hugging Face demos or other cloud services instead to install it on my own machine. Okay, so let's go to the Hugging Face transformers. First, let's see the code here. This is a simple code that you can see how to use the Hugging Face transformer. I probably should use it in a notebook style, but okay, let me do it in this way. Let me make sure it is the model I'm going to use. No, this is not the file I'm trying to use. Okay, I'm using this file instead. Let me first check my GPU usage. Okay, it's good. Let me start with it here. So first, I'm using transformer from Hugging Face to run our models. So you can see that I import the transformer and I input the, let me first try the GPT-2 models, which I will try some newer models later, but let me first try the GPT-2 model. I use torch to set the gradient, to disable the gradient here. It is like the no grade context in when you use things like with torch.noGrade. It's kind of like this one. Instead, it works for globally for a whole for everything. 所以我们这边用 set grade enable false 把那个gradient 把它关掉。虽然不是很重要啦，因为它后面做的事情大概都会帮你做掉。但是我习惯就是如果在像这种类似 notebook 的环境要用 PyTorch 的时候，如果我没有做训练，我这边一开始就会把它关掉。Okay, so let's first load the GPT-2 model. I'm using GPT-2 LM head model from pre-train to load it. I will show you other ways to do similar things, but first, let's load the model directly. There are two major interfaces for Hugging Face transformers. One is using a model or other encoder separately. The other one is a pipeline. It has a concept of pipeline. The pipeline is considered to be more high level. However, because our purpose is to explain it in more detail, so I'm using a more low level way to do that. After we load the model, you can see some you can see some basic information like the model LM head. This is one of the weight a layer in the GPT-2 model. You can actually explore and see how the models looks like. This is also another great tool for you if you want to implement from scratch for like a GPT-2 or other models, because you can run the models layer by layer and you can check the result of your implementation and the output result of the Hugging Face transformers. 所以当你想要重新实作在别的机器上，或者是比方说好了，你想要在 Rust 上面重新做一次 GPT-2 或者 Llama 你的或者在 FPGA 上面跑，你想要重新实作，其实你可以在 Hugging Face 的 transformer 上把那个模型 load 进来，然后一层一层的跑。像我们这边就拉了其中的 LM Head 啊，其他的部分，你可以一层一层的。它有2个模型的 LM Head， 然后还有一个 transformer 这个地方，你可以一层一层的跑，然后比较它的不同的结果。所以这是可以帮助你实作，就算是你不去 trace code， 这中间也可以帮助你去实作，还不错的一个方式。Okay, so our model here we have already loaded, and you can see just like other PyTorch models, when you simply see the representation of this model, you can see the different layer of it. You can see that there is WTE and WPE. They are embeddings, which we are going to talk about it in details when we demonstrate our GPT-2 implementation. They are time embedding and like a position embedding, token embedding, and the position embeddings. And also, you can see other attention layer, projection layer, and attention. It has dropout, but the dropout has no function when you do the inference. So we are not going to implement the dropout in our implementation. But you will see other layers like seems to be very familiar layers like C-attend, C-project, and LN2 MLP things in our implementation, and also in Capacity's tiny GPT or min GPT implementations. 所以另外一个方式就是从这个 model 你直接把它印出来，这是 Python 的representation， 然后 PyTorch 的习惯就是会把它的内容都印出来。那你可以看到这边有 WTE、WPE， 还有一些 dropout 在实作上面，因为我们只做 inference 不会看到，但其他的像这些 C、ATTN、C、PROJ 你都会在比方说我们的程式码或者是 Capacity 的程式码里头看到这些东西。它完全是用一样的名字，因为很多东西都是从 OpenAI， 就即使是 Capacity 去看的时候，它也会参考 Hugging Face 的 implementation， 还有 OpenAI 的 implementation， 那这些名字都是互相的是沿用的。好，let's move this model to the CUDA, and let's also load the tokenizer. We will talk about the principle, the algorithm behind the tokenizer, maybe in next week, because I believe the content is enough to fill out the time slot of this week. So maybe we'll talk about tokenizer in next week. But what tokenizer do is we are not working on the text directly. There are many ways to work on the text. One is to do it in character level, alphabet by alphabet. That's one way to do that. The other way to do that is in word level, like one word or two words, like this is a pen. So the first token should be this, and the second should be is, and the third should be a, and the last one should be pen. However, if you are using a word level tokenizer or word level language model, it has a drawback that it requires a dictionary. and people are going to has misspelled or invented new words. So that make the language model kind of obsolete or at least less effective. If you are working with character level, it can work for everything, but it is more difficult to develop a language model for character level. So people choose the mainstream is using a automatic tokenizer, since it analyzes the text in the training data and kind of making a conclusion and develop its own dictionary. So every word in a dictionary is not in the same sense of the word in our natural language, but it is just using some algorithm and the statistic to combine frequently used combination of characters together. So that's called tokenizer, and so it can work with other languages. For example, in Chinese, Japanese, or Korea, every character in Chinese is in fact represented in a Unicode. So it will contain several different bytes. And you know, there are a lot of different kanji characters in Chinese character or in Japanese kanji. So it is quite impossible to include every character or every word in a dictionary. So it turns out in the popular language model like GPT-4 or maybe like Gemini, they have their tokenizer, and a lot of Chinese characters are not in the list of tokenized. Instead, they use partial of the Unicode bytes as a tokenized. So sometimes they are not correctly construct a faded Chinese character. So you can see some something that doesn't actually invalid Unicode when you generate things when you're using like ChatGPT or Gemini, especially if you are using Chinese language or Japanese language. 好，所以我们这边讲一下 So the following translation to in Chinese will be longer because we have to talk a lot of things. 好，所以我们接下来要说明一下为什么要用 tokenize。其实你在直觉上基本上两个方法去使用去处理文字。第一种方式就是我们一个字母一个字母的去处理，这个叫做 character level。那下一种叫做 word level， 就是一个字一个字一个字的去处理，像是 this is a pen， 那你就 this 是一个， is 是一个， a 是一个， pen 是一个，那我们就可以去处理它。那不管你用 RNN 还是用其他 transformer， 任何处理 sequence 都可以处理。可是 word level 有一个麻烦的地方，就是你需要一个字典。那你的字典如果太小的时候或者不完整就不能用，而且基本上你不可能建造这种字典，因为字典你常常会发明新的字，或者是大家会用一些奇怪的拼法比方说 Kubernetes 大家可能拼成 K8S， 那这就不可能之前新发现的。那有时候是一些流行用语都会新出来，那有的时候就是你不小心拼错了，可是拼错的字就不读嘛，这也不行嘛。所以字典其实它的用法很局限，你只能在早期比较小的时候就是一些实验性质的一些模型的时候可能可以使用，但在实用方面它是不足的，特别是如果是有中文、日文、韩文这种东西它更不行弄。那如果是 character level 的话，如果是在英文这种，它的麻烦就是它不好训练，因为你光是要把一个字拼出来就需要一个字拼对，这件事情就变成它一个困难的地方了。好，所以折中下来就变成了 tokenizer。好，那 tokenizer 是怎么做呢？它基本上就是把你所有的东西看成是一个 byte 一个 byte 一个 byte， 就中文字、日文字那些东西，它是一个 Unicode 嘛，但它中间有好多 byte， 它基本上就是一个 byte 一个 byte 全部去看它，然后把比较常结合在一起的 byte 它连在一起，变成新的 token。好，有一种做法就是用 BPE 那种做法，基本上就是把最常见的把它组合在一起。那有一些是反过来切的啊，那是另外一种。好，那我们下一次会讲。那不过基本上它就是把比较常连在一起的字，它就先组合成一个它所谓的 word 啊，就是 token。然后如果两个 token 又很合在一起又很常见的话，就把它组合在一起。所以它自己有一个 token 的 list。这也就会造成说中文字像这种很多个 unibyte 的东西，而且中文字又特别多，中文的词又特别多，所以它可能不会把所有的中文字都放在它的 token 里头。特别是训练资料中文、日文、韩文比较少的时候，它特别会这种现象。所以很多中文字，它很多 token 其实是半个中文字啊，因为一个 Unicode 可能要3个 byte 才能跑出一个中文字，或者4个 byte。那看你的编码。那可能就把其中2个很常用的那个东西，它就连在一起，就开头2个。那所以真的要把中文字凑出来的时候，它要把前面2个配上后面那个 byte， 才会凑出一个中文字。所以它有时候会弄错。你在使用 ChatGPT 或者是 Gemini 的时候，你如果特别是使用中文或者是日文、韩文特别是中文，因为它的汉字特别多那有的时候会出现一些乱码或拼不出来的东西。这就是因为它其实本来就是把它组合在一起，那有少部分机会它的组合错误，所以你会看到乱码。你用多的话，你就会看到一些乱码，就是这个原因。Okay, so since we are using token, so not only we can use token to represent the word or characters in natural language, also we can invent some special utility or functionality tokens. So for example, you can see that here we have an end of text. This one is a token. Although it is composite with a very long sequence of characters like these symbols, 2 symbols at the beginning and 2 symbols here, kind of like a tag. But this one is a single token. As the name suggests, this token is represent the end of the text. So you can also have the start of text, or when you do the conversation things, you can use a token to indicate that the role has changed to another. And you can use a token to indicate the beginning with a conversation, the end of a conversation, or using a token to indicate this is a system prompt, the system instruction, or other kind of things. For example, if you are using a multimodal model, there will be tokens to indicate, okay, here is the beginning of the image, and here is the end of the image. And there will be other tokens and things that related to the image representation, the representation of the image content, because that requires some other because we require we need some to inject the information of images into the language model so that the language model can handle the content of the image. 所以我们在这些既然我们用了 token， 所以我们可以定义一些特别功能性的 token， 像是这个 end of text， 它就是一个 token。然后你可以定义一个句子的结尾，或者是如果在对话里头角色的变换，或者是一个 system 的系统的 instruction， 你可以定义让它可以方便的把它弄出来。像是其他像是 utility tool use 或者是 function code， 它都有一些在不同的地方它会不同的设计但是你比如说像 Llama 就有在 function code 它有一些特别的一些 token 告诉你那个东西是这样子。那其他像是 multimodal 的模型，像是你要进语训图形然后你要把那个图形资讯进来，它都会对应到不同的 token。那图形的内容你也可以设计 让它的那个对应到有意义的东西上面去。Okay, so let's try this one on GPT-2. So let's give a simple prompt and the instruction, because I'm not sure this GPT-2 has been instructional, it has been tuned to follow instruction. But let's just try this as is. Let's try it use a transcript of a chat. Let's just call it a transcript of the chat between user and AI assistant. And I'm using two assistants like user assistant. And I am asking the ChatGPT2, I mean GPT-2 is not ChatGPT2, it's just GPT-2. I'm asking the GPT-2 to answer this question: What is the highest mountain in the world? 好，所以我们来试试看 GPT-2 来它的能力。虽然 GPT-2 没有被像是 Chat 训练成 Chat， 或者是去根据我们的指令去做事情，它没有做 instruction tuning， 它没有做 Chat tuning， 但是它只有训练就是文字接龙而已。它就是文字接龙，跟你前面一段文字它去预测后面，就像是 auto regression， 它只有训练这样子。但是我们还是可以试试看，让它来做对话。比方说我这边就尽量的给它一些指示，然后我这不算是指示啦，因为我猜想它的训练集中可能会有一些像是 transcript 或什么，像是一些互相对答的一些内容，像是剧本的一些对白啊那些东西的，所以它还是可能用文字接龙方法来做这件事情。那我这边给它 user 和 assistant 互相问答的情况，而且呢，我在 assistant 回答这边我还给它一个开头，让它可以更稳定的去回答它，因为毕竟它没有被 fine tune 过。So because it is likely that the GPT-2 is not fine tuned by the instruction or chat for a chat task. So I'm actually giving it the prefix of the answer so that I can limit or kind of forcing the assistant to answer the question, not just doing something else. You can try it without this line. And you will see that why I need to have this, sure, the highest mountain is, why I need to have this prefix. Okay, before that, let's first encode our prompt. 好，所以我们先来把我们的 prompt 做 encode. 我们这边是原始的文字，那我们要先转换成 token， 就像我们刚才说要转换成 token。那我们用了 GPT 的 tokenizer。每一个地方的 tokenizer 是不一样，它都已经预先训练好了一个算是字典的 tokenizer 的 token 的字典。那有一些演算法让它把文字换成 token。So let's use the GPT-2 tokenizer. The GPT-2 has a predefined tokenized token list, predefined list of tokens and an algorithm for doing the tokenization. So let's just use it. Okay, so let's see what is our return from the tokenizer. You can see that it has a tensor of numbers. It is a sequence of integers. So each number, each integer indicate a certain token in the list of a token list. In a list of token list. And it also has a attention mask. This is involved with the where attention should towards, so that we can give it in the model generate. Although we didn't send a mask into this function. However, this is indicated that the things that you can provide it for the function model generate. 好，所以我们刚才是把这个 encode 把它 input 把它弄出来，然后你可以看到它就是出来一堆数字，那这些数字就是对应到它有一个表格了，那个表格其实拉得出来的，我这边可能没有弄出来，但这个拉得出来，然后你就知道第几个是对到第几个，它完全是对得到的。 Before we actually go to the model generate, let's first see let's encode let's put it into the we can actually transback this. I probably should do it right here to transback to translate the index back to the word. But instead, here what I will do that later definitely. But here we just put it into a batch. I'll just put it into a batch, so that we can get different result, 3 different results. 好，所以我们这边把它做一个简单的处理，让它变成在一个 batch 有3个，然后我们可以得到3种不同的回答。So let's run the model. So model generate X and token. So when there is a pipeline and which wrap the model generator and the tokenizer, and it handles the output, everything for you. So it is even more useful for you if you are trying to chat with the AI, chat with the model, because he handles when to end the generation. But we are using the more low level to actually see how it works. So when you use the model generate, it basically just doing the basic thing. You only give the padding and something like how many new tokens it should generate, and something like do sample, do top K. These are some parameters for selecting the result when generating a result. Okay, so after we generated the things, let's see what we get. So get the Y here. So in fact, you can see the result of Y. It is also sequence of integers. 好，所以我们拿到这个产出来的结果 Y 的时候，你可以看到它就是一堆 integer， 然后 integer 就跟我们前面的 tokenizer 出来的那个整数是一样的。Just like the integer sequence when we do the tokenizer. So we can trace back, because it is not human readable. So let's trace back it to the English text. So here's what we do. We use tokenizer decode YI to see what it is. You can actually decode one token at once, like Y14. It is like 8537. 我们其实可以一个 token 一个 token 去 decode 也是可以的。Then we can use tokenizer to decode. You can see this one is just a chat. And we can actually access to the list of tokens if you simply go inside the, let's go to a definition like here. If you trace back to the code, you can actually access to like these are something like the special tokens, and it actually has a token list, like a vocabulary file. This is a vocabulary file, so it has a vocabulary file, and JSON load encoder vocabulary handle, vocabulary handle. Okay, so you can actually access to the, because this is a vocabulary file, so you can actually access to the that file as well. But right now we simply use the decode. 好，所以你刚才可以看到，就是我们其实可以去，你只要简单的跳到程式码里头去。我这边用的是 GD 啊，就是因为我用的是 theme 的 key pointing，所以你按下 GD 就是 go to definition， 你就可以跳到它的程式码去，很快就可以找到说它哪边是它的，可能文件也有了，但是看程式码比较快。当然你可以问就是你可以问那个，你可以问 AI 啦，就是这边 Ctrl I 之后，你可以问 Copilot 或什么的，我要怎么去从 Tokenizer 去看它的那个 tokens 的 list， 你可以问它了。但是我刚才就直接找的话，也是蛮可以找到。那现在更简单，就是你直接用 decode 就可以看到它这个字是什么了。比如说是第5个字，你可以知道 between。好，那我们全部一起来看一下。Okay, so let's see the whole output result. So we have 3 different results because this is not the pipeline. We are only generate the raw results. So it didn't handle the chat interaction. So you can see that not only it generate one answer, like sure, the highest mountain in the world was mountain of the mountains. And it also generated the following conversation, like what is your name? And a lot of different things. Kind of like really like a transcript for like a movie or a film or a video. And so the first one definitely not good enough. And the second one is also not helpful. Sure, the highest mountain on the earth. So if there's anything you could help, tell me. It doesn't help much. And for the last answer, this is our last hope. Sure, the highest mountain. Okay, it doesn't have. It is the most useless answer so far. 所以他这3个回答其实都并不好，他都并没有回答，但是看起来都像是那么一回事。你可以甚至回答一些东西，然后完全不知道他回答什么，会跑到 ice cream 上面去。可能山比较高，可能比较冰一点点吧。Okay, so all these 3 answers is not helpful. Maybe we can try it again. Let's try it again. Let's try it one more time and to see. Because it is not always that useless. Sometimes it is actually useful. Okay, let's see a result. Because I think if you recall that when GPT-2 published, people kind of thinking GPT-2 is quite large and intelligent, and it's kind of very surprised how good the GPT-2 is. Okay, so but even we try 3 more, it hasn't got the correct answer yet. Okay, so it's not very easy to do that. So let's also indicate why we need a better model and using the chat fine tuning. 所以很遗憾的就是这3个回答它其实都回答并不好，可能还可以做一些事情，因为还是我这个模型稍微小了一点点，因为它可以回答还可以的答案了。它可以其实有办法回答还可以的答案。那说不定我们等一下自己实做的时候，我们让它回答一下，说不定可以看到比较好的答案，但是上面的答案其实并不好。好 ，OK， so why do I even need this one? I don't need this one. Okay, so let's try some larger model, more modern models. First, let's try Llama 3. This is Llama 3, the original Llama 3.0. And we will try the Llama 3.2 also. Finally, we'll try some Taiwanese models like Tide, T-A-I-D-E. The original Tide. I think it has an updated version, but this demo was made by last semester, made in last semester. So by that time, this one might be the most popular, the most updated Taiwanese models so yet. And also, this one is newer because I just edited it. These two, the Llama 3.2 and the Breeze 7B Instruct model. So we will see them first. Maybe we can see the tight model last, because I believe I already removed it, so it will have to download it again. But first, let's try the Llama 3 8B. Instead of just coding the GP2 like what we did for GP2, because this one is a more modern model. So, we use auto tokenizer and the auto module for causal LM. So it will determine the actual loader object for you. 所以我们这边为了要试不同的模型啊，然后而且它比较现代一点，所以我们这边用了 auto tokenizer 和 auto model for causal LM causal LM， 它会自动帮你找到对应的。其实它还是有一个那个 object， 因为大部分都是拉玛啦，前面这每个都是拉玛，它其实还有一个 loader 在那边，但是因为它说都是拉玛，所以它都是基本上这几个应该都同一个，应该全部都是拉玛去跳的。但是如果不是拉玛，像 Gemma 那些东西，它其实会这个东西也会帮你自动去找一下。好，我们先试试看这个模型。好，我们把它自动的读进来。那我们这边使用的 bfloat 16，这边其实有参考它 Hugging Face 上面的 repo。So we are using a D-type bfloat 16. There will be some choice between the approach type D-type. Most time you're going to use float 16 or bfloat 16. They are not compatible, but some modern models, especially for the Llama model, they are using bfloat 16. And because they are already tuned for or cast to bfloat 16. So if you cast it to another type like float 16, it will lose precision. It will perform worse. So, but you will get some complaint right here. So it will say, okay, it is in bfloat 16, but you are casting it to float 16. So just be careful of watch out for this error warning message. They are helpful. 所以有的时候我们会把它弄成 float 16，就是16bit 的 float， 有的时候是 bfloat 16。那大部分拉玛它都是一开始的时候它就会用 bfloat 16，因为它存进去的时候，它的大小如果是刚好是，比如说它是 7B 模型现在 8B 模型那如果它的大小大概，你看它档案大小 16B， 那它大概就是 16bit。那 16bit 有 bfloat 16，也有 float 16。你从一个转换成另外一个，它的精度会消失，会那个被破坏掉。那它会在拉玛这边，它如果你帮它转成 float 16的时候，它会丢一个 warning 给你，你就会看得到。那你也可以从它的 Hugging Face repo 上面，你可以看到它是怎么用的，你就可以知道它比较适合的形态应该是什么。那另外转成 int 8或者是其他的什么4bit 的，那就要看它是怎么去转的。我们这边先暂时不去看这件事情。好，我们现在把它 load 进来了。So let's see the device, because we are using auto device map. So it is a good idea to first check what actually device it defined. Or you probably should use like CUDA if you are trying to use it on CUDA. If you are using auto, I will suggest that always check the model device first. So here I have some template that I'm trying, a simple template that I'm trying to see the reasoning of the reasoning, the logic capability of the model, to test the capability of this logic capability of model. So I'm using the last one. The last one is kind of like a trick question. 好，所以这边是一堆我之前先设好的一些问题，用来测试语言模型的逻辑性。那最后一个这个是一个有点像是陷阱题。So the last question is, I have $300 bills. $300 bills. So I have 100, 100, and 100, $300 bill. When I went to a restaurant, after a meal, the check was like $170. The bill is 100. I have to pay $170 bills. I paid the check with cash using the bills I brought. The waiter then gave me back the change. What was most likely the amount of change that I received? Maybe I should using I'm just saying with cash. Okay, it might be less misleading. Okay, so the correct answer should be, if you are trying to use 300 subtract 170, it is not incorrect, because you'll get 130. But when you bring like $300 bills, and if the meal is cost you like you have to pay like 170, you probably will only take 2 of the bills to pay, and you will get like $30 change. So the correct answer for this trick question should be $30. 好，所以这是一个有点像陷阱题啊，就是我带了300块，我带了3张100块钱的钞票去餐厅，然后要付170块，那我会拿到多少零钱？当然你可以300减掉170等于130了，可是因为你正常来说你应该只会拿200块去让他找钱嘛，所以你拿到的找钱应该是30块，而不是130。那当然不是说130是错的啦，没有法律禁止你拿300块去付钱嘛。那所以，但是我们可以看看他会怎么回答就是了。So it is not illegal to pay the bill with $300 bills, and I think the clerk will still give you a change like $130. But this is a trick question, so we can still see what happens. Okay, so let's run the models, and we have some terminators right here to indicate, to let the model knows when to end the generation. 好，所以我们这边用了 terminators， 等一下会放到这里头去，让这个模型知道什么时候来结束它的对话。不然的话它也是一样会一直生下去嘛。即使它已经 fine tuning 过，它其实还是会一直生下去的。那我们告诉他说这个 AOT ID 这个地方就是要结束了。Okay, so let's see the output. Recall this one is for Llama 3, the original Llama 3. And it actually do the mathematics correct, like 300 minus, like 3 times 100 is equal to 300. It is very aware that it is not a 300 bill. It is 300 bills. It is not just one 300 bills. It is 300 bills, and it computed correctly. But it fall into the trap that we shouldn't pay 300 bill. We probably would just pay 200 bills. OK， 所以他算对了，300算数都对了，就是3乘上100，还有300减170。他也完全理解说这是3张100元钞票，而不是1张300元钞票。只不过他还是去回答130就是了。所以这个当然你还可以继续说，我们真的需要把3张都问，你可以再接续对话了。但是就我们测试的结果是这样子。So let's try some newer models to see whether it works better. Let me try the second one, the 3.2 3B models. Spoil a lot that it probably will answer the same. Okay, it's kind of too slow. Maybe I loaded too much models. Let me restart it and run it again. Let me run it again. Let me make sure the memory is cleared. Okay, it is cleared. So let me run it again. But this time is for the 3.2 model. Okay, you can see that even with the 3.2 model, but this one, to be fair, it is a smaller one. So it's actually will have the same answer. So let's try the Breeze model, which is come from MediaTek, to see if it is getting smarter or not. So this one is a 7B model, and from MediaTek, the latest model from MediaTek. 好，所以我们试试看那个联发科的那个 Breeze model， 看它会不会更聪明一点，而且它是 7B 的模型，它是新的 7B 的模型，它也是回答一样的问题，回答答案，所以我们最后再试试看那个，看看要不要试这个啦，因为它可能会漏得有点久。OK， so because let's try the Tide model, the Taiwan's model, but probably I'm not going to try it because I remove it, so it has to. But you can see this is how it works. Usually, if you try a new model, it will download automatically for you, so you can see the progress bar. But currently, how many times it is going to use like 2 minutes more? It is it takes too long for us, so I'm going to abandon this experiment. 好，所以因为你可以看到它新模型的时候，它需要下载了，但是因为这个下载还2分钟，我觉得太久了，我们就先不试它了。So instead, let's try other questions and to see how it works. Let's try some Chinese prompt. This one is pretty much says that Xiaoming is 6 years old now. His sister is half his age currently. So we know that his sister is 3 years old. So the question asks, when Xiaoming is 70 years old, how old is his sister? So it is supposed to be like 67, but a lot of AI previously will answer something like 35 because he take this his sister is half his age literally. So let's see how the AI works for this trick question. Let's first clear the output. 好，所以我们来试一下刚才那个小明的问题，然后看他会不会掉到陷阱里头去。好，因为刚才那个问题他们算是掉到陷阱了嘛，那我们来试试看这个问题。OK， 好，我现在把那个问题读进来了。OK， so let's first try the MediaTek model. Let me make sure what model. We are trying the MediaTek model. Okay, so let's see the result. Okay, interesting. Okay, so it says that we know Xiaoming is now 6 years old. So after 70 years, Xiaoming will age like 76 years old. And because his sister is half of Xiaoming's age. So after 70, so this is just totally wrong. It's plainly wrong. If you are assuming it is 70 years after 70 years, why you are changing it to 76 years? And makes totally no sense at all. Okay, so it is a fail. It is a fail. So let's try another model. Let's try let's go to here and try llama model, the original llama model. I could not find it here. Okay, let's try the llama model, the llama 3.2 model, and see how it goes. So for llama 3.2 model, okay, it is still totally wrong. It says 9 years old. It's kind of a surprise. I haven't tested it for this new model, this question for new model, but I know sometimes they are going to have something like 38, 37, 32, but these two answers are just plainly wrong. Let's try the llama 3 8B model, because I have tried it before and it seems to be quite okay. So at least sometimes it will answer correctly. But the reason I'm trying this question is because in my experience, the new AI model kind of works on these questions. So maybe I'm not sure, but maybe I have. Okay. It takes quite long, maybe because no, they still on CUDA. So maybe I have there are also some other trick questions like, suppose I have 3 apples and I put one in my left hand. How many apples do I have? And another trick question is that I have 3 cars and I drove one of them to a restaurant yesterday. How many cars do I have? You may try it as well. But okay, it's too slow. So perhaps I should reload everything and rerun it to give it a fair chance to answer a question. So let me try it again. So this is our last hope to get a correct answer for these 3 models. Okay. Yeah, although the Llama 3 answer in English, but at least it answered it correctly. 67 years old. So I think we probably still need at least a 8B model to make it to be have some sense of logic, some ability for reasoning. 所以我们看起来需要那个就是模型逻辑能力有的时候会需要大一点的模型啊。那 3B 看起来一般表现还不错，就是 3.2 3B 大部分表现还不错，但是在逻辑上面还是有明显的一些差距。即使我们用旧一点的模型 3.1 还不错啊， 3.1 跟 3.2 不会差很多，但是3其实是有差的。可是即使是3的模型，它 8B 它这个问题有回答正确，但是我们刚才的那个 3.2 3B 没有回答正确。所以这是你可以观察到的一个现象。Okay, so finally, let's try using the pipeline. Let's try the 11B model, vision model, to answer the same, to answer some simple question for image. So you can see that I'm using a pipeline right here instead of using I'm using model. I'm not using pipeline. Okay. The pipeline is right here, but I jumped to the last one, to the multimodal model. But let's first see the pipeline. A high-level usage, or maybe the most popular usage of the Transformer API is using the pipeline. 好，所以我们一般来说，其实你比较常见的会用 pipeline。那刚才 generate 算是一个比较低阶的，你要先 tokenize 啊，然后 generate 啊那些东西。但是通常我们用的是 pipeline， 它可以整合你的 model。这个 model 可以放 model ID， 也可以放你先 load 进来的 model。哦，这样子的话可能会比较不会占用空间啦。虽然我相信它应该都有处理这些问题。不过你这边是可以放一个 load 进来的 model， 那也可以放 model 的 ID。然后它可以做比较，它有点像刚才 generate， 但是它可以比较整合这完整的事情。好，所以我刚才也是问一样的问题，好，就是 restaurant 那个问题，然后它可以直接用 pipe 的方式解决它，然后你不用去做太多的事情，因为它本来就会。我们现在 pipe 你可以看一下这个 pipeline，是 text generation， 然后还可以做不同的一些 pipeline。Okay, so the higher level API is pipeline. So this is probably the API that you use more frequently. So just for reference, the reason that we use generate low level API is to demonstrate how it actually works step by step. Okay, so lastly with in this demo we see the VLM, the visual multimodal language model. 好，所以我们现在来看一下这个 multimodal 的模型。我们这边用的是 Llama 3.2 11B Vision. So let's use the Llama 3.2 11B Vision instruct. It is quite a good model that can fit into a consumer level, consumer grade GPU card, specifically 4090, 4090 or 3090 cards when it has 24 gigabytes memory. 所以它可以放得进24G 的GPU 卡片里头去跑。当然你可以用 CPU 跑了，那24G 也蛮适合，就是你很容易你的电脑就会有32G 以上的记忆体，然后就这个也都可以跑。那当然你记忆体更小的话，你用 quantize 的版本。So if you have like 16 gigabyte memory or like or less, you can probably try a quantized version. I believe you can find it on Hugging Face repo. You can see that here, right here, we are using an image that we download right here. Let's see what this image is. Okay, so here is an image that we are using. It is Pete Rabbit 所以这是彼得兔嘛所以我们把那个图片我们来看了一下。And you can see that we are asking the AI to, if I had to write a haiku for this one, it would be about this image, of course. 所以我想要写一个那个日本的那个他就写一个这样子一些句子，然后 a rabbit in a coat so fine, so it right here. A rabbit in a coat so fine, walking down a dirt path, springtime's gentle breeze. Okay, and then you can see that here's a special ID for the image. So it inserts the image right here. And it has also other tokens like begin of the text, start header. This one, the header is the user, and this one indicates the role is assistant. It actually answers the question quite well. We can also ask some simple questions like So let me ask it another question. What is the animal inside the image? Describe the image. Let me just ask it to describe the image. This one is actually easier than the one that we just used, but anyway, it is a quite a good demonstration. So you can see that it showcases a charming anthropomorphic rabbit standing on a dirt road in a picturesque countryside setting. The rabbit dressed in a blue coat or brown. I believe that you can ask it to describe it in more detail. In more details. We can also ask it to use the Chinese to do the answer. Okay, I'm asking it to use the Taiwan's traditional Chinese to answer the question. Oh, okay, it doesn't answer it in Chinese. Let me force it to do that. Okay, let's see if it works. No, it doesn't work. Maybe I should ask it in Chinese. I mean, in general, Llama 3 can answer and understand Chinese, but yes. 这是一个英国乡村道路上行走的巨型兔子。So this is a giant rabbit walking on the country road on England. The giant rabbit wearing a something. It doesn't answer it. Okay. So, but at least it can answer it in Chinese. Okay, so that's the first demonstration. So if you want to find out more models, you can search the Hugging Face. You should search the Hugging Face. Okay. You can search Hugging Face models. So here you can search it quite easily. Like the new Omniparser model from Microsoft or Diffusion, Stable Diffusion 3.5, and the Mochi one. Mochi one is for the text to video generation. It is an open source one and quite good. And also the Flux. Here are all the most hot models recently, available recently. And so, for example, if you want to search like Llama 3.2, and if you want to search things like 4-bit, vision. Okay, 3.2 vision instruct 9B, but it doesn't have. There are also some texts to do the quantize, like but I couldn't find it, like GU. So there will be some these labels are also quite useful, but unfortunately I couldn't find the one that I want, because you can actually search model for like 4-bit quantized or even like maybe 3-bit quantized. But I kind of forget the keyword or the text that we probably needed. Maybe AWQ. Oh yeah, it has like here. You can find like int 4 AWQ models. There are different ways to do a quantization. You can use that as a keyword to search a model that you want to use. Okay, finally, let's go to the next part. The next part, we are going to explain the transformer. Let me close this one. Let's explain the transformer and our implementation. So let's go to this. You can find the link to the implementations in our course page. In our course page, which is llm.tjwei.tw. Okay, so this is a repo for the code I'm going to use, the gp2.py, this one. So I'm going to explain how this code works. So first of all, I'm not going to implement the tokenizer. I'm using a pre-written tokenizer, that is tick token, because we're not focusing on tokenizer, and the tokenizer is a bit difficult to write because it uses some regular expression. The difficulty is not the algorithm itself; it's the way that they split the word. They usually use a regular expression to split the word first, then apply it to the tokenizer. But the regular expression has some compatibility issues you need to address. It is sort of difficult to implement it correctly. So I decided that since this is not our focus, I'm just using the tick token instead. This is the same approach that used by the Kapasi's approach. Firstly, he developed a tokenizer to explain how tokenizer works, but finally he gave up and used a tick token instead in his later main GPT, I believe. Okay, so first of all, let me write it line by line. Maybe I should use, I'm not sure which one I should use. Okay. This one is a tokenization for GPT-2, but I'm not going to use it. Okay, I'm using a GPT-2, but I'm going to run it line by line and explain it and compare to the paper. Okay. The output is not important for most of the part. The most important is how to the expression and the relation between this guy and the. So let me arrange my screen. Transformer attention is all you need. Paper. So the paper is attention is all you need. Let me first explain the transformer architecture a little bit. The full transformer architecture has a encoder and a decoder. And in the GPT style AI, it only has decoder. 所以 transformer 其实有 encoder 跟 decoder， 但是 GPT 它只用了 decoder。所以我们只会讲 decoder. So we only talk about decoder. And so the most relevant part is a transformer self-attention, the self-attention and the multi-head self-attention and the transformer block. So they are using transformer block only. The GPT is in fact just to stack multiple transformer blocks together. So we have a lot of these blocks and we stack them together. And before this transformer block, 好，所以那个 GPT 就是一堆的 transformer block 叠在一起，然后没有左边的，它没有 cross attention 这个东西，它就是直接这一块把它叠在一起。那我们等一下会帮它做个对比。And before the block, there is a embedding part. So it has a positional encoding and output embedding. There are generally several different ways to do the positional encoding. One way to do that is people use the learned encoding. 好，所以这边 positional encoding 是用来标记那个每一个字在什么位置，因为 attention 本身它跟位置是无关的，所以你一定要把位置的资讯把它放进去里头。Because when you do the self-attention, the attention itself does not contains the information about the position of which the token is at. So you need to encode the position encoding. There are different ways to do the position encoding. One way is to just use it as a learned parameter. So 所以一种方法就是让它就是反正我就放在那边嘛，然后让它去学它的位置。那所以它的位置如果有我们假定它的 window 是1024、2048，那这个东西留下来之后，就你有2048个向量让你去学它的东西。所以超过一定就没办法用了，因为它就是大小就是这么大，你就是学起来了。So the drawback of to learn the weight is that the context window is fixed because there's no way you can extend the positional encoding. Another way to do that is to use like sine, cosine, trigonometric encoding. So use a pattern to predefine encoding. 好，所以另外一种方法就是有时候常会用三角函数、正弦、余弦函数，用不同的频率的正弦、余弦函数，先定义好，然后就用这个东西去用，然后有不同的方法来用。好，但是我们在做 inference 的时候就不重要，因为反正我们就是从那个表里头把它的那个 positional encoding 把它读进来。But since we are mostly focusing on the inference, so either way, we are reading the positional embedding weight from the checkpoint file. Okay, so the important part is the transformer block and for self-attention mechanism. So what is self-attention? The self-attention is as following. We project a vector. So given a vector right here, we project this vector into three different kind of values. To use a linear transformation. This is just a linear transformation into three different things, three different vector. One we call the query, and another is called the key, and finally something we call the value. So the idea is that the KV, the key and the value, kind of like a dictionary in Python. And our query is something we want to find the value from the dictionary. Right? You just give the Q. Suppose you have a dictionary right here. It has a key value pairs. So the thing is, when you give a query, you simply find the same key. Key equals to query and find the value and return the value. This is called like a hard query. This is kind of like a hard query. 所以self-attention 其实就是有点像是 Python 的 dictionary。你有一堆 key value 在这边，有点像，但我们等一下要讲不一样的地方。有一堆 key value 在这地方，你这是你 dictionary， 所以你得到一个 query 的时候，这个 query 目前因为我们叫 self-attention 嘛，所以它这边就是简单的从一个向量，我们把它分成三个，做线性变换分成三个。好，那这个 query 我原则上要做的事情就是，我每个向量都这样子。那我现在有一堆向量，因为你现在想象就是我现在可能有100个向量，我要去做 self attention，那这个 self 指的是这100个向量的东西。那每一个向量我都是做一个线性变换，得到它的 Q， 得到它的 K， 得到它的 V。那接下来这一堆 KV， 我们现在有一堆 KV， 这一堆 KV 形成了一个 dictionary， 这一堆 K 跟 V 形成了一个 dictionary。那我在每一个向量我都会做一个 query， 那这个 query 我就要问说，我要从这个 dictionary 去拿出哪一个 value 出来。那假如如果它是硬的，我们等一下讲软的，它其实是软的啦。如果是硬的 query， 就是我这个 Q 去找到那个相同的 K， 那我就把那个 value 拿出来。可是问题是我们现在的 Q 不会找到一模一样的 K， 那怎么办呢？我们做的事情就是做内积。你看这边是什么相乘嘛，然后 scale， 然后 max 是因为我们只能往前去看而已。因为我们现在想象这是一个 sequence， 每一个只能往前去找，所以要做个 max。但基本上我们就是跟前面所有向量，我的 Q， 我现在这个 Q 对不对？我跟前面所有的 K 去做内积，得到一个值。好，那如果你要用硬的话，就找最大的，因为它最像那个。但是我们要现在做软的，所以我们用一个 soft max， 我们不找最大，我们用 soft max， 它是软的。然后呢，找到之后呢，我们就等于是有个权重嘛，不是找一个，而是找它的权重。然后所以我们就把它找到的所有的值，依照它的这 soft max 得出来比例，把它加权总和。所以它不是找一个值它是找到一个软的 query，就是它 90% 像第一个， 5% 像第二个， 5% 像第三个。那我不是只有找第一个值出来，我是 90% 的第一个值加上 5% 的第二个值加上 5% 的第三个值。Okay, so it mostly works on a sequence of vectors. So each vector we got its Q, K, and V. So all of these K and V forms like a dictionary. So when we do a query, you can imagine that we have a new vector here, and we got its Q right here. When we do a query, we simply check how likely, check the similarity between this Q and K. We simply use a cosine similarity. We simply use the dot product to sort of like a cosine similarity to see how similar between this Q and this K. But instead of doing the hard query, if you want to do the hard query, you simply find the max one because it has the max similarity. Then we take the value. That is called the hard similarity, hard query. But we are trying to do a soft query. So instead of find a hard max, which is simply the max, we do a soft max. It is the same soft max that you use for like classification models, because that they came from the same reason. We want to do a soft max. So instead we do a soft max. So we probably get so that, okay, this query is 90% like the first one, 5% like the second one, 5% like the third one. So instead of just picking the first value as our output, we are doing a weighted sum. So we take 90% times the first value and 5% times the second value and plus the 5% times the third value. So we got a weighted sum. So this is our output. So the final matrix multiplication is the weighted sum, and the first matrix multiplication is the softmax. It's a softmax. It's an inner product. And we'll talk about scale. Scale is used for like because if you have a longer sequence, your inner product is going to be bigger. If the value is going to be really big, the softmax is not consistent, because when you do softmax, you are doing exponential, so it is going to be really large. So we have to have a scale to kind of kind of discard the effect of to deal with the effect of the different lenses。好，所以这个 scale 我们这边基本上前面最后这个 matrix multiplication 是做的是加权总和，然后这边的 matrix multiplication 是做的是它们的内积。那这边 scale 等一下会讲，就是原则上就是因为你的长度向量长度越长，它乘起来内积就会越大。那这越大，我们最后在 softmax 我们会送到它的那个softmax 我们会送到它的那个exponential 的函数里头去。那 exponential 很大的时候，那个你的 softmax 就基本上会变成 hardmax。我们已经设计好的东西，我们不希望发生这种事情，所以我们会做一个转换，让它不要这么夸张。好，然后and finally the mask is because for every factor we are doing the same thing to query and check the more similar factors before it. So we are kind of dealing with a time series. Everyone is only referred to the previous tokens. So we have a mask to do so. Because we have to do the matrix multiplication since altogether at once. So we're using mask to filter out the tokens after it to make it like no effect at all. So this one is a mask. So this one is the self-attention, single head self-attention. So you can check that this one is the scale. This one is the force this is the whole formula right here. This one, dk means the dimension of the key. So because it's getting longer, we want it to be getting smaller. And by some consideration computation, we take the square root of it. 好，所以这边就是刚才的 scale。我们 dk 就是 k key 的 dimension， 因为 key 的 dimension 跟 q 的 dimension 必须要一样，它才内积嘛。那它内积的那个长度越长的时候，我们希望它的作用被中和掉，所以我们把它除以它。但是为什么不直接除以它？因为这是经过计算的，我们就除以根号它。好，除以根号它。Okay, so this one is a full formula of the single head attention. However, because attention is kind of mimic the intuition of the relation between this token and the other tokens, we probably will try to find different relations between words. Like let's consider a simple sentence like he kicks a ball. He kicks a ball, and we want to find the ball and the relation between for other tokens. So he is the one who is doing action to the ball, and the kick is the action that applied to the ball. So both he and the kick have some relation to the ball, but they have different relations. So we probably want to mimic this behavior. So there are different relations between a token to others. So maybe we want to do this attention multiple times. So this is called the multi-head attention. This is called a multi-head attention. We do this multiple times and concate them together. And finally, we do a linear mapping to get the final output. 好，所以因为有的时候我们文字跟文字之间的关系不是会只有一种 attention 是用来代表说这个文字跟哪个字有关。那比方说好，他踢球，他踢一颗球好了，他踢一颗球，那这个球跟什么有关？它跟他有关，因为是这个球是被他跟他互相有关系嘛，他去踢球嘛，所以他们是两个关系的物体。踢跟这个球有关系啊，踢是一个动作，我们作用在这个球上的动作叫做踢。一个跟这个球也有关系啊，因为代表这个球的数量，所以文字跟文字之间会有很多种不同的关系。那我们就做这个刚才那个 attention 很多次，每一种我们希望他最后学到的是不同的关系。那这叫 multi-head attention。那最后它每一个我们就各自做嘛，做完之后把它的结果 concate 在一起。这个长度太长了怎么办？我们就做一个 linear 让它缩小到我们想要的长度。所以这叫 multi-head attention。 好，所以这个东西右边你看到的这个东西这边有点放到太下面一点点了。Okay, so you can see this one is multi-head attention. This guy is the most core part that we're going to implement it. So just remember this graph, and we probably will see it later. Let me first move it to here. Okay, so here is a code. Let me explain the code, and we probably will see the graph a little bit later. The first part is the parser for the safe tensor, for safe tensor format. Instead of calling safe tensor files, there are some modules for reading safe tensor weight. I'm implement it from scratch. So here is the implementation of reading the safe tensor. It is still quite interesting, but I'm going to omit it because our focus is mainly on the GPT implementation and the transformer implementations. Okay, first of all, they are using a norm called layer normalization. Let me try to see where it is. Okay. So if you see the building block of attention block, there's one thing called the norm here. They are using layer normalization. They are using layer normalization. And using a residual architecture here, and using a layer normalization. Layer normalization is for convergence, because you may have used a lot of like batch normalization, but here they choose to use layer normalization because some people have some consideration for batch normalization. So in particular in here, the GPT use layer normalization. I mean, they are just this is just a choice. It's just a normalization. It just happens that they choose the layer normalization. So we have to implement layer normalization right here. 好，所以其实它就用什么 大家有用不同的 normalization 了。那只是刚好这边 GPT-2 它是用 layer normalization 所以因为一定要有一些 normalization 比较好收敛了，所以我们就用 layer normalization。那这边就是完整的告诉你什么叫做 layer normalization。我们进来的 X， so here is the full algorithm and formula for doing layer normalization. For the layer normalization, it still has a W and a B for its weight and bias. It's kind of like a linear transformation things. So when you find a layer, first we normalize in this way. We normalize layer by layer. So you can see here, we normalize this. For each layer, this input have different layers, so we take the average for the second axis. 所以这边你可以看到，我们这边基本上就是把它先做 normalize， 先减掉它的平均，再除以它的那个标准差。这个 square root of variation. The square root of variation is the standard deviation. So we subtract the mean and divide it by standard normalization. So we normalize the X for each layer. And then we learn a W and B, so we multiply it to W and B and get our final result. So this is layer normalization. And we also define a linear layer, which is pretty much the same as the linear layer of like PyTorch or like TensorFlow. But because we are using NumPy, so we have to define it by ourselves. And as you can see, it is quite simple to do that. Unlike this W times W, Xn times W plus B, this is a multiplication element-wise, and this one is doing a matrix multiplications. And also, what does it mean by embedding? Embedding is just lookup table. And embedding is just a lookup table. 好，所以我们这边也实做了，除了实做 linear， 也实做了 embedding， 让你可以知道它真的是怎么跑的。所以 PyTorch 和那个 TensorFlow 他们其实都有实做这些，但是他们实做其实很简单。那你可以从这边实做的缺点，大概可以知道说为什么他们要做比较复杂的实做。但是本身它的数学上的算式是很简单的。比方说 embedding 就是一个查表，它其实就是 lookup table。所以你看到一个 weight， 不要觉得它是一个很复杂的一个操作，然后觉得这个黑盒子干什么？它事实上，如果你在 Python 来看的话，就是我现在这是 array 嘛，我就是查表。所以像刚才 positional embedding 或者是 token embedding 那一些所有 embedding， 它既然学完之后，剩下来你去做 inference 的时候就是查表。你是第5个 token， 它就看第5个向量；第7个 token， 它就看第7个向量。比那个 attention 那个 query 那个更直接，因为它就是直接查表。这个 linear 也是这样直接做就可以了。So embedding is nothing but lookup table. You don't need to kind of afraid to seeing the code because they are just as simple as this one. We also implement the activation function Guru that used in GPT-2. I forget why they use this and what is the importance of this Guru. There are a lot of different activation functions like Siru, Iru, Liru is a more ancient one. But I'm just implementing it and using it right here. It's sort of like the Riru, but smooth Riru. But there are a lot of different activation can be considered as a smooth Riru. But anyway, we just implement this Riru because we need to use it. And also we implement the softmax. If you have learned what softmax is, this is just an implementation. I'm implementing it in this way, like I first minus the maxima of it and take the exponential. It's because whether or not I minus the maxima one, mathematically the result will be the same. However, if I do this operation first, it will be more numerically stable because we're going to take an exponential right here. If the largest value is so large, the sum of them might be very huge and might be kind of going to infinite. 好，所以你看到这边就是 softmax 的实作。那如果你知道 softmax 是什么的话，你可以读一下，就是完全是跟它实作一模一样，跟数学式子一模一样。如果不知道的话，你可以回去查一下 softmax 的数学式子，然后跟这个实作比一下。如果你比较会读程式，而比较不会读数学式子，你可以看它。但是会发现我第一行做一个特别的事情，就是我减掉它最大的一个。数学上来说，你减到这最大一个，你最后除掉之后会是一样的答案。但是我会这样做的原因是因为它的数值的稳定性就是 numerical 的 stability 的问题。因为你如果不这么做的话，它数值有些会太大，它加起来之后可能会超级大，那就会让这件事情会整个数值上计算不稳定。所以这是一个常用的一个技巧，先扣掉它最大的东西。好，这是 softmax。Okay, and this is a utility function two heads, because we have n heads. We implement a multi-heads things. So this operation use a lot. This use a lot. Because when we do a linear things, we probably will do this linears at once. But in fact, we want to this is another thing like here. So in principle, we want to use a linear projection for Q, a linear projection for K, and a linear projection for V from one single vector for each vector. However, because all of them are linear, so it would be easier to do just simple linear projection to 3 times the dimension and then split the vector. So we do this kind of thing a lot. So this two-head thing is doing a similar thing. We split one vectors into different vectors. Okay, so here is our major the core part of this implementation, the self-attention. So first we have a CATTN. You can see that we have a CATTN. This is a linear mapping that's mapping the attention. And we have a C projection, a CPROJ. We also have a CPROJ. And also we have embedding. The number of embeddings. That is the dimension of K, Q, and V. They are the same, but we need to have a number right here. We calculate from the shape of the weight, because like we said, we do just single one linear projection, so we have to divide it by 3. 所以我们一开始有定义了这个 C attention、C projection， 然后还有先计算一下它的 KQV 的 dimension， 然后这边就直接从 weight 去计算，然后因为这个东西 weight 它只会做一次 linear， 就是 C attention 这个是我们读进来的嘛，这 C attention 就是刚才那个 attention 的 projection 那个东西就 attention 的那个 linear 的东西，所以我们直接把它除3就可以得到它个别的 dimension， 然后我们也可以得到它有多少 head， 就是 n head 是我们前面就已经拿到的东西。So we also have the number of heads and each head dimension, we get the head dimension. And also we have the mask computed so that we know how to do the attention. And we also have to speed up the computation, we also have to catch the K and the V. So this is also, if you read the implementation of other things, you also get the KV catch. That's pretty much the similar things. Okay, so here is a logic. I am writing it in similar to the format of the PyTorch or like the customer class in TensorFlow and Keras. So we have an initialization and a forward part, which we use directly use the call. Okay, so first, when we get an input, we use C attention to get a Y. So this Y, our first input will have a batch size and the sequence length and the dimension of embedding. This is our input vector. Then we do the self-attention. We'll get KQV, so the size between becomes n embedding times 3. 好，所以我们进来的东西有 batch size， 你的那个 sequence 的长度，还有你的 KQV 的 dimension， 好，就是 n embedding dimension。然后呢，我们这边呢用那个 map 去把它做 projection， 得到了KQV， 所以你这边看到这边变成3倍了。And then we extract the batch size and the sequence length from the shape of Y for convenience. And we split the vector into KQV part. And because we are using a multi-heads, so we further split the KQV into multi-heads setting. Because each KQV is going to be multi-heads. So we are splitting this KQV to make it to become multi-heads things. So we split each vectors into smaller vectors. This if incremental is to do the it's basically to do the speed up. Is what we are trying to do is to speed up things to have a catch things of that. So when we find out that our sequence length is just one more, then we speed up the computation. So we kind of ignore it right now. And also this one is also for speed up because we have a K and a V to update our cache. So our attention map, we compute our attention map using the Einstein notation. Because I couldn't find the right production formula, functions in NumPy library. So instead, just compute it in the Einstein notation. So you can see that BMHD, BNHD, and to get a BMHN. So we keep the batch, we keep the M is a sequence length, what we get is for different head size and dimensions, and this is what we get for the K the QK here, this is what we compute for Q here. And also we have to do this guy, to divide this guy. Divide it by this guy. So we get this one. The square root of the size of head dimension. So this is our attention map. And we simply compute the mask, apply the mask right here. So our attention map is, we get our attention map from the softmax. And finally, we do the final reshape and do the projection to the Y. So we get the final result. Also, this is you can check pretty much everything right here. So this one is a follow. Before the loop, there's this guy. We do the the scaled dot product. 好，所以前面大部分就是在做 scaled dot product attention， 然后我们做 multi head， 每个都有做了嘛。然后最后我们再做一个 projection. So this is a final projection. And we get our Y. So this is simply just following everything described in the transformer paper. That is, attention is all you need paper, and we do the implementation. There are a little bit details for speed up, like we have a cache. Other than that, it is just follow the formulas one by one, step by step. 所以你基本上你要是扣掉那个像这种 incremental 啊 cache 啊，剩下来的东西基本上你可以看到，就是他要叫我们做 attention， 我们就做 attention map， 然后技术上我们要把它分成多个 head， 我们就把它分开来了。而且你可以看得出来它怎么分成不同的 head， 因为那个读起来可能你会有一些不同的想法，但是这边可以很实际告诉你它的 head 怎么分，它就直接把我们得到 KQV 把它切开来啊，就这样子而已。然后最后就是 attention map， 实际上计算如果有 batch 的时候，它就是这个矩阵乘法，只是我们的 batch 有那个 sequence size， 然后这边有它的 mask， 我们就做它。So here's a mask, here's the QK multiplication, and finally we combine the weighted sum 啊，所以最后我们不是把那个 phi 跟那个 attention map 算出来那个 attention map 把它整合在一起吗？哦，就是这个最后一个 matrix multiplication， 这是这个地方，哦，就是这个地方。哦 ，so here is the last matrix multiplication for a single head one, and finally we reshape everything, put them together. This one is a concat one, this one is a concat. This one is a concat. This one is a concat, and finally we do the last linear projection. So this one is a linear. We pretty much get everything step by step. Nothing more and nothing less. Okay, so after we got our self-attention block, we can put them together into a transformer block. So what is our transformer block? So let's compare to this picture. I think I probably has a better one, but I forgot to bring it right here. I have a slide, so for a better one here, but we can still look at this one. Okay. the graph right here. So basically we have multi-head attention, max multi-head attention, and a norm right here. And finally we have a we don't have the one, we just feed forward and output it. So you can see that we have a linear layer 1, linear layer 2, and attention, and the last MLP. The MLP is the feed forward thing right here. Okay, so as you can see that what we do is we first use a linear transformation, apply on this X, we do a linear transformation. And then we do the self-attention. And we add X to it. So you can see this is the add thing here. This is add right here. So I have to have X add this guy. And then we do the last block, which we do MLP and the linear here. This is the feed forward network here. And we still have sorry. The LN is not linear, it's layer norm. It's a layer norm. We do a layer norm on X and we put it into attention. You can see it right here. We put it into right here. So we do a layer norm first and then put it into the attention block. And then we have another layer norm. So this is like an add norm. We put a norm right here. This is add norm. Add and the norm. So we add right here and the norm right here. And we add here and the norm right here. We're doing it twice. This is add and norm. Because the block is followed one by one. So okay, I think my camera start dying, so I remove my camera.所以基本上我们就是把这个第一层跟第二这个东西结合在一起。那这个我刚才讲错了，是 layer normalization。这是 layer normalization。所以你看到我们先有个 layer normalization， 然后多过 attention， 然后加上 x。这个加 x 其实就是这边的 add。然后在下一层的时候，我们又做一个 normalization。这边其实就是 norm。这边就是 normalization 的 add and norm 的第二个 norm。好，然后我们再把它 add 上去，所以跟它的图有一点点不太一样了。但是因为它叠在一起嘛，所以它还是有 add 有 norm， 只是顺序可能需要稍微厘清一点，有点不太一样。但每一层基本上它就是在做这件事情 ，layer normalization attention， 然后 add layer normalization attention， 然后再 add， 就是在做这件同样的事情。所以这就是一个 block。So this is essentially, but although they are a little bit different, maybe the order of the norm and the add, because if you look from this graph, we should have a norm first, then add to it. But we're adding something before the norm. We're adding something before the norm if we are looking at its implementation. So they might be a little bit different from the original. Attention is all you need, but they're pretty much very, very similar. So finally, we put all the blocks together to get our GPT network. So first, we have a WTE, that is a token embedding, and a positional embedding. And we have developed our context length. Because the positional embedding is trained on a fixed length, so we can get the information of the maximum possibility of our context length. If we're more than that, then we cannot go beyond this context length. 所以我们先拿到我们的 token embedding 跟 position embedding。从 position embedding 我们就可以知道，因为它的 embedding 就是它查表嘛，它的位置总共有多少边嘛，所以我们可以知道它最多可以到什么大小，所以我们就得到我们的 context length，context 的长度。 那我们一开始的 mask， 我们整个 mask 就是一个三角的矩阵，因为每一个东西就只能看到前面的东西嘛。So also said our mask is a triangular matrix because every token can only see itself and every token before it. So it will effectively form a triangular matrix. So we define our mask in this way, and okay, so we get our the heads, how many heads of it, and blocks. Okay, H is the weight. Okay, H is the weight. So we construct our blocks. So because GPT is stack several different transformer blocks together. So we read our information, the spec of our blocks, and we stack them together to become our self.h. And finally, there is a layer norm and the LM head to finally do our output. Because we have to do one of our output, we'll see how the output is going to be. So how do we actually output our token? Okay, so here is the logic. So first of all, we get our input sequence. And we should output it one by one. So before that, we first run the block one by one to get our output. So get our x here and run our x equals to block x. So basically, we run through several attention block. So we run through several of these guys. And finally, the things is getting a little bit different, but we will see it. We are not going to run the softmax. We are going to run a different way to output the token. But before that, everything is the same. We first run the as you can see, we first run the positional encoding and put them together. We add the positional encoding and the token encoding, adding them together. So you can see that we add them together. We not concat them, we add them together. 好，所以一开始的时候，我们先把所有的那个 positional encoding 和我们 token encoding 都算出来，然后把它加在一起。直接相加哦，它不是叠在一起的。这是我们的 input sequence。那接下来这个 sequence 我们就经过这个 block 把它就跑。这 block 就是这一堆 block， 我们就进去跑。所以你看到前面就是 embedding position encoding 加在一起，这边真的是加哦，然后进去以后跑这个 block 跑，全部跑完。So you can see that the position encoding is added onto the output encoding, and then we run through a bunch of blocks, transformer blocks. And finally, after we got our final output, we put a layer normalization first. And 所以一开始我们先做个 layer normalization， 我们反正最后这些 block 得到 output， 我们得到 layer normalization. And last, we do a simple multiplication. I mean inner product to the LM head. head. 所以我们最后得到的 output 是 x 嘛，然后我们就跟我们的 LM head 去做一个内积。LM head 是就是它另外的一个东西，这边是另外我们有读出来一个叫做 LM head 的东西。LM head 的作用就是你要去找用来做最后 softmax 去找那个你要的东西的，但是我们只是先算 logit， 我们先不算 softmax， 我们先算 logit。好，所以那边基本上就是最后一个 linear 在做的事情。So this LM head is basically the last linear thing. So after we get the GPT, we get the ML head, we multiply our output to the ML head. So this one is corresponding to the last linear part, We haven't do the softmax yet. So in here, we are going to do the softmax or do the probability later, because we want to have some freedom to like adjusting temperature or adjusting how many like a top K like top K set selections. So we probably will keep logic instead of doing the softmax directly. 所以我们这边有先做的这个 linear 没有错，但是我们会先不做 softmax， 因为我们保留这件事情到我们之后可以调 temperature 啊，可以调那个你的候选的，你只选前面40个啊，避免尾巴的那个干扰这件事情。Okay, so that's pretty much of it. So let's first run the code here. And then we actually load the model. So let's load the GPT-2 XL. I have already downloaded it. And let's load the largest GPT-2 model right here. It has 48 blocks, maybe, and the dimension of each vector embedding is 1,600. So we got everything right here. And we should run it on here. Then we do the logic and the selection right here. First, let's run the code because it will take a while. It will take a while. We also ask what is the highest mountain is a similar question. As you can see, it is not that slow, even though we only do a naive implementation. But you can see that the highest mountain is Mountain Everest. So that's why I say GPT-2 can answer this question correctly. So I'm kind of confused why it didn't get it correct in our last 6 trial. Maybe we didn't use the XL model. We used the medium or the smaller models. But I'm not sure. But GPT-2 already has the capability of answer the question of which is the highest mountain. 所以你看到它其实已经回答，还并不是那么慢了，不是很快，但是也不是那么慢。而且你看它回答正确了。我们之前那6次试验都失败，可能是因为我们用的不是那个最好的、最大的那个 XL 模型啊，不是很确定。但是至少你知道 GPT-2 有这个能力去回答正确的东西，它还是可以用的。而且我这边还没有特别设定啊，我这边只有设定 user 跟 assistant 而已。Okay, so let's see how we actually pick the token that we use. So after we get the logic from our GPT output, we divide by temperature. So temperature is the setting. If you have a larger temperature, everything is going to be quite close to 0. So everything is going to be more likely to be choose. 好，所以你除以它的那个 temperature， 如果 temperature 超大的时候，所有东西都会接近0。那你做 exponential 的时候，等一下都会接近1，所以每一个 token 都会更加的可能被选中。So if you have a large temperature, you can make the model more creative. Making it more creative. If I have a little temperature, it will make the choice more sharp, the decision more sharp. So it will have more regular and more correct answer. 所以如果 temperature 很小的时候，那个每个数字变大。所以等一下那个softmax 的时候，所以你用不同的 temperature， 你会得到它不同的那些正确性和它的创造性之间可以做个取舍。好，所以我们这边得到 probabilities softmax logic， 然后你可以看到这边的话，我们就 sort 它，然后我们选，因为这 sort 是反向 sort 啦，越大排越后面。那我们把它前面的那个，就是我这边选的是 DK 大的东西，然后不如 DK 大，我就把它直接设成0，它的几率直接设成0。So the first part is implementation of temperature, and the second part is for top K. So I only pick the most likely top 50 most likely tokens here. So I arbitrarily setting the value to be 0 if it is not in the top 50. If I didn't do that, there will be a small chance it choose some token that is really likely. It is because we are using softmax. Even though we think it is very unlikely, it still gets some chance that is greater than 0. We probably intend it to have a smaller chance. So people often use top K to improve the quality of the language model. 因为如果我们不做 top K 的话，有一些几率非常小的 token， 因为它非常多嘛，但是 token 非常多，但是很多几率非常小，他们被选到的几率还是挺大的。那这个东西就我们可能不太希望发生这种事情发生，因为实际上它应该要更小了，但是因为我们用 softmax 来用这种计算，它没办法那么小，所以我们每一个字下一个字有50的可能性已经很多了嘛，所以只要超过50，我们直接去掉，让它变0，让我们的最后能够回答的品质变好。Also, I'm using top K and the temperature to improve our inference quality. Then I simply use the softmax here because I'm already taking the exponential, and this one is essentially the softmax. I didn't use the softmax tricks to improve the numerical stability. I probably should do that, but okay, no, I already used the softmax because I already used softmax right here, so that numerical trick has already been applied. But I'm simply kind of normalize the probability so that because I kind of discard some element that with small probability. So we are doing here right now so that we can make it to become the probability even if we discard the little guys. 好，所以这边基本上就只是因为我刚才丢掉一些东西嘛，所以我让它还是加总是1，这样我才可以用 random choice, so that we can use the random choice with the p equals probabilities, because we have to make it the summation make to equal to 1, and then we use this function to choose our next token. So that's all. That's the whole process. It's one of the simplified, but it uses 2 of the common techniques. One is temperature, and the other is the top K heuristic. 好，所以这是一个简单的算是 inference 的方式，但是已经用到2个常用的技巧，像 temperature 跟top K 这种方法。好，我们再帮它跑一次，它会跑出不同的。好 ，so let's run it again. It will show different result. It should show different result. So in the second chance, it didn't answer it correctly. It answered the mountain is a snow line. I am not sure if it is a real mountain, but at least it answered the question. And I'm definitely know it is not true because it says it is 15,000 meter, 15 kilometer, and it is from the South Pole. It is not correct. But anyway, this is how the GPT-2 works. And basically, GPT-3 is a large scale GPT-2, and GPT-4 or ChatGPT is another story because they do some instruction fine-tuning and human feedback, reinforcement learning, human feedback, reinforcement learning things. So that will be another story which we are going to talk about in the next 2 weeks. So that's all for today's lecture. 好，所以我们今天就讲到这边，然后之后我们会再介绍一下比较更进阶的技巧，而且你大概知道现在这个东西怎么跑的，你会知道我们在讲它比较理论的时候，你可能知道说，哦，这个东西为什么要有这些东西。好，那以上就是今天的内容。